Hi, everyone. Thanks for tuning in. I'm going to talk about our work on scalable RSA modulus generation with a dishonest majority. This is joint work with Megan Chen, Karmeet Hazai, Yuval Ishai, Yuri Kashnikov, Daniele Michancio, Tariq Riviere, Abhi Shalat, and Ruhan Wan. What's an RSA modulus? It's simply a product of two primes, also referred to as a biprime. Since its inception for designing the first public key encryption, RSA has found use in several cryptographic primitives, most recent of which has been for the design of verifiable delay functions and more recently, zero-knowledge snarks. I'm going to talk about verifiable delay functions as this has been the motivation for our work. Introduced by Rivest, Shamir, and Wagner, a related primitive called inherently sequential functions requires that a function be only computable sequentially. No matter what space you have, the only way is to compute it sequentially. So consider this function where you're repeatedly squaring mod n, where n is a biprime. The only way to do it is to do it in t steps where you square g repeatedly t times. And this was conjectured by Rivest, Shamir, and Wagner. More recently, this inherently sequential function has been enhanced to also get the verifiable property by two excellent works by Purchak and Veselowski independently. They showed that once a function is computed at a certain point, you can also attach a short proof that can be verified very quickly of its validity. So this works if this inherently sequential property works only if this biprime n is of the form that no one knows its prime factors. So the goal for us in this work is for the world to have an instantiation of a verifiable delay function based on an RSA biprime. So the goal is to sample a biprime n where the factorization is hidden. And we're going to use an approach that is, time tested for doing such an approach. I mean, short of having some secure hardware do this, the only approach we know of is to use a secure multi-party computation or MPC. So what's the desiderata that we, put forth for this setup ceremony to generate a biprime? So we wanted to generate a modulus of size 2048 bits for a threshold of n-1 corruption, meaning an active adversary can corrupt all but one of the parties. We want to scale it to over 1,000 parties. I should say that in this dishonest majority setting, there hasn't been any work that has scaled any non-trivial MPC at this scale. We wanted the parties to be lightweight and their bandwidth to be small. And we will tell you a little bit on what in our implementation, how we instantiated the parties. And finally, we set the statistical security parameter to be 60 bits and the computational security to be 128 bits. So here is our protocol blueprint to design a secure multi-party computation for the distributed generation of an RSA modulus. So this is a popular and most common approach to design concretely efficient MPC protocols. First, you design a passive protocol, and then you enhance it to get an active protocol. So let me walk through the steps where I'll tell you how we design our passive protocol and then follow it with our active protocol. So we need a passive protocol that scales, and as I mentioned, to over 1,000 parties. And let me tell you that this is a very thriving area of research. This problem was introduced in the seminal work of Bonnet and Franklin in '97 of precisely this task, giving an MPC protocol to sample an RSA modulus. And there have been several works improving, in different scenarios. We are interested in the dishonest majority setting, and here you can see the work of Hazai et al. And the work of Chen et al. Work in this. And I should point out that only the work of Hazai et al. In fact implemented any MPC to generate an RSA modulus. But our work will be more close to the work of Chen et al., who introduced really, a very nice idea to improve the efficiency of these protocols, among other things. So here is the Bonnet Franklin framework. Besides maybe one previous work, all the others follow the Bonnet Franklin framework, which roughly proceeds as in 3 steps. The first step, you sample numbers for prime candidates. Okay, so basically parties choose additive shares for prime candidates. Then in a second step, they multiply these prime candidates to get candidate biprimes, and in the third step, they test whether these are biprimes. Now, to improve efficiency, even starting from the original work, they considered some versions where they can eliminate certain prime candidates just easily, like if they were a product, if they were a multiple of 2 or 3 or of small primes. Okay, we are going to follow the Chen et al.'s blueprint, which is based on the Bonnet Franklin blueprint, but they do a very clever modification of the first step. Instead of sampling prime candidates and sieving them for removing those divisible by small prime factors, they gave a mechanism by considering these numbers in the CRT representation, Chinese remainder theorem representation, to automatically sample candidates that are already not divisible by the small primes. So this just improves the complexity and increases our chances of sampling a prime number. Another thing that was, crystallized in the work of Chen et al. Is that essentially to design a protocol in this framework, all you need to do is you can reduce it to designing just the secure multiplication functionality. In fact, all these 3 steps can be reduced to secure multiplication, especially in the passive, but they also have a similar theorem in the active version, but we are going to focus first on the passive version. And the biprimality testing additionally requires a distributed version of the Jacobi test, which doesn't require secure multiplication, but it just works, and which is used by all previous works. Okay, so what is the secure multiplication functionality? In fact, it's an extension of what is called oblivious linear evaluation, which is a generalization of oblivious transfer for arbitrary fields. So what does the secure multiplication function do? Well, parties have shares for 2 numbers A and B, AIs and BIs, which they want to compute the product of summation AI and summation BI and obtain shares for the product. Okay, this is an extension of the OLE functionality that I mentioned. So how does one implement secure multiplication functionality? Well, you can reduce it to OLE, which is a 2-party functionality. But the main drawback of reducing it to OLE is that then your protocol is going to scale quadratic because every pair of parties need to use this. A better alternative is to use the threshold additively homomorphic encryption, which actually scales linearly in the number of parties. We're going to use the threshold additively homomorphic encryption, but with a twist. We're going to introduce an additional party that we call a coordinator. Okay, this coordinator is going to facilitate the parties being lightweight on their spec. Okay, which means that this coordinator, in fact, is going to take some of the heavy part of the computation as well as the communication. And this coordinator doesn't have to be trusted. In fact, it will be a verifiable coordinator. We can publish and we can just have the entire view of this coordinator open, so that you can test, you can check whether it proceeded correctly during the protocol. And what this allows is that now the per party communication actually scales logarithmically in the number of parties, and this is truly makes our protocol scalable. The second step, as we mentioned, is to compile to full security. And in the past decade, there's been several works on doing this step and improving the efficiency, moving from passive to active. There have been really beautiful techniques. But what we are going to do is we're going to revisit the classics, and we're going to say, we are going to try to use the classic GMW paradigm, which roughly proceeds as follows. You have an multi-party computation protocol. You first commit to your input and randomness, and then you supply a zero knowledge proof at every step of the protocol. Okay, now this is traditionally, this has been, at least in the concrete efficiency literature, this approach has been dismissed primarily because the zero knowledge proofs are really heavy. I mean, even with the improvements in zero knowledge, doing this in every step is going to be heavy. Nevertheless, we show that this approach, in fact, can be applied to the protocol, the passive protocol that we are doing. And we want to observe 2 things. First, there are no inputs in this. There's only randomness because you're just sampling by primes or sampling candidates. And the second thing is it's enough to attach one zero knowledge proof at the end of the protocol. This is because, even if during the protocol someone deviates, they can violate privacy. At best, they will learn the other party's randomness, but will be caught at the zero knowledge at the end. So, if this happens, you identify this party, kick this party out, and restart the computation. There is no private inputs privacy that is violated because there aren't any private inputs. As we mentioned before, we are going to introduce a new party called the coordinator. This coordinator only performs public operations. That's why it's verifiable. Like I can publish everything that this coordinator is doing, and a third party can come and audit it later. And then we're going to have every party sign every message. And finally, we can put the entire transcript on a bulletin board. And this additionally also gives a public verifiability feature of our protocol. Imagine that we generate an RSA modulus this year. Next year, someone else would say, like, I am not sure, like, how did you generate it? And they can go to the transcript, they can see the identities of who all participated and can verify the computation to make sure that, in fact, the biprime that was sampled is indeed a biprime. So now let me just fill in some of the details on how we instantiate our primitives. Let's talk about the threshold additively homomorphic encryption. There are several choices. We chose the ring LWE because it supports packing. We can do several multiplications in parallel, as well as it has a very easy setup for key generation. This is the most efficient construction. The zero knowledge constraints that we had to use in enforcing, like I just wanted to kind of say that this was a complicated zero knowledge statement that we wanted to prove. It had ring operations. This is from the lattice space. Then we needed to consume the triples, but these were triples mod several prime numbers. So it was not just over a single field. And finally, we had to also prove some correctness in the Jacobi test, which was modulo some the target RSA modulus. So what zero knowledge protocol did we use? Well, we needed something that was memory efficient because we wanted a lightweight prover. The parties had to prove their actions, and we needed something that was communication efficient. So we used a sublinear transparent zero knowledge snark. We instantiated with Ligero because it had some nice properties. For when you have several repeated computations, the Ligero system has some nice features. But we also had to attach another protocol which is efficient for exponentiations in the RSA group. And this was a Sigma protocol due to Shu. So, and then we had to combine these two to make sure that, there were witnesses that spanned both these zero knowledge, and we had to prove some stitching constraints. So this is, I just wanted to tell you some of the features of our protocol. We got security with abort up to n-1 party corruptions, and the coordinator by an active adversary. And our coordinator is verifiable, so we don't have to trust the coordinator. Finally, we have identifiable abort because it's based on zero knowledge. Anyone who fails their zero knowledge, we can identify and kick them out. And also, again, we get public verifiability just by parties signing their messages. So let me talk a little bit about our implementation. We instantiated our parties with a T3 small instance from AWS, which has 2 CPU threads. And a coordinator, we use the best machine because this, this is verifiable. It's okay to, and we just need one person. If we are running the ceremony, we could have, a coordinator to, we can choose the spec of the coordinator. So we used one with 96 threads and close to 1 terabyte of RAM. And we had some we used the FHE standardization to select the parameters for the ring LWE and a public key infrastructure for signing every message. So let me tell you quickly about our performance. So for 2 parties, the passive took 20 seconds and the active took 10 minutes. And if you notice that as we increase the number of parties, the passive and active scaled really nicely. Like in fact, these numbers should not change. I mean, they increase slightly, but then after you can see that it actually, goes high. So if you look at 1,000 parties, we took about 6 to 7 minutes for the passive part and about 20 minutes, 25 minutes for the active part. And I want to point out that actually the bottleneck here is not the parties, because the parties' computation and communication doesn't change with the increasing the number of parties. It's the coordinator, and we use the best machine on Amazon. And in fact, if we considered a distributed set of coordinators that could distribute the load, all these numbers would go very close to the 2-party setting. So the bottleneck here is the coordinator, which is a nice thing. So in summary, we designed the first scalable multi-party computation with a dishonest majority and a practical implementation of the generic GMW paradigm. I wanted to point out that from passive to active, our computational overhead was like 4 to 8 times because we just attach a zero knowledge proof. And again, the communication is just twice because we used a sublinear zero knowledge proof system. And the bottleneck is the coordinator spec. And we also had a new kind of functionality to give us a modular proof of security. Thank you.